Hi, I'm Naomi, and I'm going to be talking about Lab 1. So for the intro, a little overview is that we observed the motion of a marker rolling on a flat surface with a constant velocity, and then we created a code to kind of mimic the motion of the marker and then predict the motion based on formulas and things. And the purpose of the lab was to compare the difference between observed motion and predicted motion. And for the experiment, the system was the marker and the surroundings were things like the earth and the table. But since it was only moving in the x direction, the earth didn't really factor much into it. And then our main results were that predicted motion and observed motion are very similar. And I'll talk about that later. So some of the main ideas were that there's no net force since there was a constant velocity. Acceleration was also zero, and so based on the F equals ma formula, F is also zero. We also use the velocity update formula in the GlowScript code, and this helped to just support that velocity was constant, and helped us update the ball's position in the while loop. And then also the position update was used in the code, and this helped us update the predicted position of the marker throughout each time increment. And average velocity equaled final velocity, which also equals initial velocity since it's constant. So during the experiment, we set up a meter stick in front of the camera on the millimeter side and recorded the marker rolling across the table. We didn't start at rest, we started with it in motion. But the marker started at position 0 millimeters with a velocity of 39 millimeters per second, which we determined graphically. And it entered the frame at 0.47 seconds, so that was our initial time. And then we used the tracker to determine the distance traveled by the marker during the time increment between each frame, so which was 0.33 seconds. So this is a picture of it. To answer the what if question, the results would basically be the same. If we switch the x-axes, it would just be in the negative, but the magnitude of it would be the same. So we would just change the code to follow that, and the comparison results would be pretty much the same. So for the code part of the experiment to predict the motion, we use the starter code and then change the velocity to the slope of the graph, which was 39 millimeters per second, and change the initial time and delta t values to the ones mentioned above. And then in the while loop, we updated the time boundary to the length of the video, which is 1.77 seconds. And we use velocity update and position update for the code. And so this is a portion of the code that we changed. Everything else was the same as the starter code. And it outputted a little position versus time graph and a velocity versus time graph, and a model for what the motion of the marker would be, which also was the same as the observed. And for our results, the predicted versus observed position, we saw that they're very similar. For most of the time increment, observed position was greater than the predicted position, but at the end, predicted position ended at a higher value. Some possible errors would be inaccurate tracking using the software, and also rounding, since we only used 2 decimal places and put it into the predicted position code. It could have caused some slight differences and also miscalculations. So in conclusion, the observed and predicted positions were very similar and demonstrated the motion of the object the same, which means that we probably did the predicted part right. And to answer the what does it mean question, I think that most forces could be determined since it's only moving in the x direction. Gravity wouldn't really factor into it, but things like friction, which is a contact force from the table, could also be factored in, and also maybe air resistance, but there aren't many other forces that could be acting on it. But I think we could figure out most, if not all of them.